Star factories at dawn. To make those early overachievers plausible, you have to walk inside the machine rooms that light them up. Not the polite, regulated factories we see later, but metal-poor cauldrons where gas collapses violently, fragments hard and burns fast. At dawn, the chemistry is simple. Hydrogen and helium dominate. Metals are scarce to non-existent. That matters because metals are the universe's coolant. Without them, gas struggles to shed heat, so collapse stalls unless a few narrow channels, molecular hydrogen lines and later fine-structure cooling from the first trace carbon and oxygen open the valve. When they do, fragmentation goes nonlinear. Clouds don't form a neat handful of stars, they shatter into swarms. In those brief windows, star formation efficiencies spike. A single cloud converts a shocking fraction of its mass into stars before feedback slams the door. Feedback is the throttle and the turbo. Massive newborns pour ultraviolet radiation into their surroundings, carving HII regions that overpressurize and compress adjacent gas. Supernovae follow on short fuses, millions of years, not tens, punching shocks that both disrupt and perversely trigger collapse along their shells. In clean gas, even modest enrichment multiplies cooling routes. One blast seeds the neighborhood, the next generation forms faster. Enrichment is a stair step, not a ramp. Every step shortens the clock. Black holes enter early as impatient foremen. If the first stars were truly massive, hundreds of solar masses, some die into hefty remnants that start accreting immediately. In pockets where gas collapses quasi-isothermally without fragmenting, aided by strong Lyman, Werner backgrounds that suppress molecular hydrogen, or by dynamical inflows. Direct collapse black hole seeds may form at 10^4-10^5 solar masses in a single gulp. Either way, a seed that lights up at Eddington or super Eddington rates bathes its host in X-rays and mechanical energy. That sounds like a quench. Sometimes it is. But anisotropic outflows and clumpy media create channels where feedback compresses cold filaments while venting through low-density chimneys. The result can be burst, clear, refill cycles that net more stars, not fewer. Simulations compress all of this into subgrid prescriptions, rules that stand in for chaos below the resolution limit. Early on, those prescriptions were tuned to Z12 disks, not Z10 knots. Retuning means letting cold streams penetrate halos without being thermalized wholesale, allowing star formation to be burstier and more stochastic, coupling feedback preferentially along paths of least resistance instead of isotropically, and boosting metal line cooling immediately after the first enrichment events. Do that, and you manufacture compact stellar cores quickly, then puff them with subsequent heating, the kind of structural evolution JWST hints at. There's a selection trick baked in that amplifies our impression. In a universe where most early systems are small and dim, surveys preferentially find the tail, starbursts caught at high specific star formation rates, or lensed overperformers that masquerade as common. Catalogs fill first with the loudest factories, the ones mid-burst, mid-outflow, mid-glow, while the quiet majority waits below thresholds. That bias doesn't forgive the tight timeline. It explains why we meet the sprinters before the pack. But even after debiasing, the ledger points to efficiency. Metallicity indicators, oxygen lines relative to hydrogen, rest frame UV slopes corrected for dust, imply quick cycling from pristine to enriched. Nebular line equivalent widths push absurdly high in some spectra, screaming young, hot, and dense. Rest optical continuum, when pinned by spectroscopy, sits stronger than naive models predicted for ages that young. If you're keeping score, those are three independent dials pointing the same direction: short depletion times and fast recycling. What about the initial mass function, the statistical mix of stellar masses? If it were top-heavy at dawn, with more massive stars than the local IMF, you get more light per unit mass and faster enrichment. That helps ease mass inferences and speeds the chemistry. There's risk in leaning too hard on it. A wildly different IMF would ripple into reionization budgets and supernova rates that other data constrain. The reasonable middle is mildly top-heavy in extreme conditions, then settling toward local once metals rise. Several groups have tested that knob. It buys time without breaking later checks. Black hole seeds reappear when you follow the light's edges. AGN contamination can inflate stellar mass fits and mimic maturity. Careful SCD modeling and X-ray limits peel off some imposters. A residue remains where AGN and stars cohabit. In those, the AGN isn't a mistake. It's part of the growth story. Coevolution kicks earlier than we thought, with bulges and black holes racing each other up the hill. There's a darker lever, too: gas supply. Cold streams from the cosmic web can feed halos continuously at high redshift, threading filaments straight through hot halos that haven't had time to stabilize. If the inflow rate outruns outflows, the tank stays full. Sufficiently dense inflows overwhelm feedback intermittently, lighting repeated bursts. In simulations with adaptive refinement, you can watch the braid. Filaments deliver, clumps form, winds vent sideways, and the dance repeats. Put it together and the picture shifts from miracle to method. Metal-poor gas that cools in spurts. Fragmentation that flips from reluctant to rampant. Feedback that compresses as much as it clears. Seeds that stir the pot instead of just boiling it off. Subgrid rules that stop smoothing the very chaos that makes early assembly fast. The factories at dawn don't need magic. They need permission to be messy. And when you grant that permission, the tension with lambdictum relaxes without dissolving. You still want a slightly shorter clock if the Hubble tension resolves that way. You still welcome modest nudges from initial conditions. But the heart of the fix lives where it always does in astrophysics. In the physics of gas under pressure, given too much gravity and not enough time. The Hubble tension and a shrinking timeline. While those star factories were doing overtime, another clock on the wall started ticking louder. It wasn't in a galaxy image. It was in the numbers we use to convert redshift into time. The question sounds dull. How fast is the universe expanding right now? The answers refuse to agree. And if the faster answer is right, the early universe had less time than we thought, which perversely helps explain why early light looks so intense. Here's the split. One camp anchors the present expansion rate, h, in the early universe. Start with the cosmic microwave background, measure those acoustic peaks, evolve a lambdictum model forward, and you get a present-day h around 67 kilometers per second per megaparsec. Add baryon acoustic oscillations and you tighten the leash. It's self-consistent, elegant, and model-tied. The other camp measures distances directly in the nearby universe. Build a distance ladder, calibrate Cepheid variables in galaxies with precise parallax, use them to calibrate type Ia supernovae, read the slope of the Hubble diagram. That ladder lands closer to 73. Switch out Cepheids for the tip of the red giant branch and you still land high. Use an entirely different technique, time delays in gravitationally lensed quasars, where variations in the quasar's brightness arrive on staggered paths, and you get values that join the local choir. Independent instruments, different systematics, same refrain, faster. This mismatch has a name the field can't shake, the Hubble tension. It's not a rounding error. As analyses improved, the gap didn't melt, it hardened. People went hunting for shared biases. Cepheid crowding, dust laws, metallicity corrections, sample selections. Tip of the giant branch calibrations to avoid the same pitfalls. Strong lensing teams built careful mass models and long campaigns to measure delays. Each method trimmed its own hedges. The tension stayed, and in 2025, new time delay results from teams in Tokyo strengthened the late time case for a higher H, independent of the traditional ladder. Why does a higher H help our dawn problem? Because a faster expansion today shrinks the inferred lookback time to a given redshift under the same model. The road marker, z equals 10, sits a bit closer to us in clock time if the local H is larger. That doesn't magically turn dwarf clumps into massive galaxies. It buys breathing room. A timeline shaved by tens of millions of years at high redshift isn't everything, but it eases the pace those factories must keep. The harder question is what physics could reconcile both camps without sleight of hand. One family of ideas tweaks the early chapter, before recombination, so that the sound horizon, the physical size of those acoustic ripples, is smaller than lambdictum assumes. Early dark energy is the headline version, a brief injection of energy density that spikes the expansion rate for a moment, shrinking the ruler. Keep the CMB peaks in place with a shorter ruler, and the same observed angles imply different distances later. Then you can raise h to match the local universe without wrecking the microwave sky. Variants play with additional relativistic species, altered neutrino physics, or features in the inflationary potential. All aim at the same lever. Change the calibration of the early yardstick so the early and late measures meet. Skeptics ask for receipts. If you add an early energy component, you can't overproduce small-scale structure or mangle recombination. If you add radiation, you affect nucleosynthesis and the CMB damping tail. The viable models thread narrow corridors between datasets. Some make it through, many don't. That's progress, not failure. The data prune the garden. Meanwhile, the local side keeps cross-checking. JWST has joined the distance ladder game, refining Cepheid photometry in crowded hosts with sharper resolution. Some calibrations nudge numbers slightly but don't settle the fight. Stronglens time delays, fully independent of the traditional ladder, continue to prefer a high H, reinforcing the discomfort. A few analyses find values that lean modestly lower. The overall picture still splits early versus late. There's a tempting narrative trap here. Declare the early universe wrong because the local methods feel more direct, or declare the latter suspect because the CMB suite is so clean and global. The honest view is less romantic. Each approach measures something real, filtered through assumptions. The tension is a diagnostic, not a verdict. It points to one of two outcomes. Either a subtle, shared systematic still hides in plain sight across multiple late-time probes, a tall claim. Or we've learned that the simple lambdictum story needs a small preface, a tweak to the opening paragraph that leaves the rest of the book intact. If the latter wins, the too big, too soon refrain softens again. A shorter sound horizon and a faster inferred H compress the timeline, making elevated early efficiency look less miraculous and more necessary. Those galaxies remain overachievers. The universe stops being broken and becomes tight on time with a more complicated prologue. Here's the human moment. A lensing team spends years chasing 4 images of a quasar that flickers with chaotic grace. The delays settle. The model holds. Their H lands high, and they know they've just made somebody's night and somebody else's rebuttal. Across the world, a microwave background analyst refits an early dark energy model against the damping tail and admits it almost works, but not quite without strain. Both publish. Neither declares victory. The clock on the wall keeps ticking, and the dawn galaxies keep shining, daring the timeline to catch up. Dark energy, dark matter, friends or suspects. If the clock might be off, the next suspects are the two actors that never show their faces. Dark matter builds the scaffolding, dark energy stretches the stage. For decades, they've been the reliable background players that make the plot work. Now the opening chapter feels tight and everyone wonders, are they still just friends, or did one of them nudge the prologue? Start with dark energy, the lambda in lambdictum. In its simplest form, it's a cosmological constant, a fixed energy density of the vacuum that doesn't dilute as space expands. That single term explains late-time acceleration, fits supernova distances, and with Bow and the CMB, sets a clean geometry. The constant version is stubborn and simple. It also leaves no room to massage the early-time yardstick without adding extra pieces. So theorists ask if lambda could be a field that changes slightly with time, quintessence, or an episode of early dark energy that spikes before recombination, then fades. Those aren't free lunches. An evolving component must pass the CMB's tight checks, avoid spoiling nucleosynthesis, and keep galaxy clustering in bounds. The viable corners are narrow, but not empty. A brief early pulse can shrink the sound horizon just enough to soothe the Hubble tension, then hand the baton back to an effectively constant lambda later. If that's right, the dawn timeline contracts a little and the first lights look less miraculous. Not easy. Possible. Now turn the other dial. Dark matter is the growth engine. Give gravity something cold, invisible, and nearly collisionless, and it collapses into halos early, pulling gas along. The spectrum of initial fluctuations, more power on small scales or less, sets how quickly those halos assemble. Within current bounds, you can tweak the tilt of the spectrum and the amplitude sigma aid a hair and speed small-scale collapse. You can't go wild without smashing the CMB peaks or lensing statistics, but you can lean into the edges. Warm dark matter, particles with a little thermal kick, would do the opposite, smearing out small scales and making early assembly harder. That's the wrong direction for our problem. Self-interacting dark matter reshapes halo cores and satellite distributions, helpful for some galactic puzzles, but neutral for the dawn factories unless the cross-section is tuned to change inflow geometry. The headline remains: cold, mostly collisionless dark matter is the right tool for fast early structure, provided you let the baryons use it well. Inside that scaffold, small parameter shifts matter. A slightly higher sigma-8 pushes more halos over the threshold for rapid cooling at high redshift. A modestly higher baryon fraction feeds denser disks that fragment harder. You can adjust within observational fences and raise the odds of catching luminous sprinters at Z 1013 without wrecking low redshift clustering or weak lensing. But each nudge pays rent everywhere. Too much small-scale power and you overproduce satellites. Too much baryon density and you bump the CMB damping tail. The virtue of lambdictum is that it ties your hands gently. The vice is that it ties them. What about the chemistry and light we measured? Enhanced early cooling through even trace metals accelerates baryons regardless of dark sector tweaks, but the timing of those traces depends on how quickly halos form and merge. A slightly quicker halo assembly, courtesy of an allowed upward tilt or amplitude, cascades into faster enrichment and brighter rest optical light, which is exactly where the tension sits. Meanwhile, if dark energy briefly intervened pre-recombination, the ruler shrinks, the distances retune, and the clock tightens. Two small moves, separately constrained, that both help. Here's where the suspects earn their names. Change too much and everything else breaks. The constant lambda has passed 1,000 consistency checks. Making it dynamic invites new ones. Cold dark matter explains the CMB peaks, large-scale structure, lensing, and cluster abundance. Trading it for something exotic usually harms early assembly, not helps it. The honest middle is flex, not flip. Within lambdictum elasticity, you can bend but not snap. And yet, even with modest bends, some stubborn signatures at dawn still insist on efficient baryonic physics. High equivalent width lines pointing to young, dense regions. Compact stellar cores that imply violent inflows. AGN that show black holes and bulges racing together. Dark matter and dark energy set the lanes. The baryons did the sprint. So are they friends or suspects? Both. Dark energy may have whispered early, then gone quiet. Dark matter remains the workhorse, with small allowed parameter moves tilting early growth. Together, they frame a universe that can deliver bright juveniles on time if the gas plays fast and messy. The crisis doesn't ask you to fire the background players. It asks you to check if one delivered an extra line in the cold open, and whether the other stood a little closer to the spotlight than the rehearsal notes said. Voids, cold spots, and missing texture. Swing the camera from crowded proto-cities to the places that look forgotten. Out in the boot's void, you can fly hundreds of millions of light years and count galaxies on your fingers. On a first pass, it feels like someone missed a render pass, like a texture pack failed to load. But emptiness isn't a bug in a universe that grew from ripples. It's what gravity does when it drains the basins and piles matter on the rims. Start with how the web forms. Inflation lays down tiny over and under densities. Cold dark matter amplifies both. Over densities grow into filaments and knots. Under densities evacuate, pushing material outward and swelling into voids. Simulations seeded with near Gaussian initial conditions routinely spit out vast hollows, rare but allowed. Survey teams slice wedges through the sky and watch the dots thin, then vanish, then reappear as walls on the far side. The statistics match what lambdictum predicts for a universe that likes contrast. The eye expects wallpaper, nature prefers relief. Those emptinesses aren't silent either. They're clean laboratories where galaxies evolve with fewer flybys, slower harassment, and gentler tides. Gas can trickle, disks can stay cold, and star formation can dawdle. If you're hunting for breaks in the code, voids offer a trap. A giant hole doesn't mean missing physics. It usually means the recipe worked. Rare isn't wrong. Rare is part of the distribution. Then your attention catches on a different kind of absence, a cool blotch on the oldest light we have. The cosmic microwave background maps look like static until you plot their power spectrum. Then they look like a drum carved by sound. Overlay that neat pattern onto the actual sky, and there's a patch a few degrees wide that runs colder than average. Analysts dub it the cold spot and spend years testing the obvious outs, foregrounds. You model and subtract dust and synchrotron. Survey masks. You rotate and reweight, it persists. One physical way to lower a patch's temperature is the integrated Sachs-Wolf effect. Photons that cross a large, evolving under density can lose a little energy if the potential wells are changing as dark energy accelerates expansion. Stack galaxies along the cold spot's line of sight, and you do find an extended underdensity, a supervoid, big enough to matter. The debate is whether it's big enough. Some reconstructions say the void accounts for part of the dip, not all. Others argue the combination fits within noise. Either way, the anomaly's significance lives in a gray zone, provocative, not definitive. Here's where the missing texture metaphor can steer you wrong. The microwave background is a random field with well-measured statistics. In any finite realization, you expect peaks and dips. If you pick the deepest dip after looking, its rarity is less shocking than the headline suggests. The look elsewhere effect is relentless. The honest move is blind tests. Define your statistic before you see the map, generate many fake skies, and count how often you get a patch as cold. Those exercises tend to deflate drama, not to zero, just to modest. This isn't permission to shrug. Anomalies are useful because they force you to audit the pipeline. Are beam asymmetries sneaking in? Are component separation methods correlating noise across scales? Are your masks biasing multipoles? Teams reprocess with different algorithms and instruments, WMAP, Planck, ground-based polarization maps, and watch the cold spot wobble but not vanish. It ends up as a Rorschach test. If you want a relic from pre-inflation, you can squint and see it. If you want Gaussian luck, you can quote numbers and move on. Meanwhile, the broader consistency checks keep earning their keep. The void size function, the distribution of void sizes, leans on the same initial power spectrum that sets filament strength. Observed catalogs agree with simulations within sensible bounds. Lensing across voids measures their mass deficits. The signals line up. Cross-correlations between microwave maps and large-scale structure detect an average integrated Sachs-Wolf imprint, as expected in a lambda-dominated universe. The missing texture, in other words, looks more like compression than deletion. You don't store many bits in empty interiors. You encode structure at the boundaries. There's a human moment in this quiet science. A grad student builds mock skies, planting artificial supervoids with different profiles. She ray traces microwave photons across them and measures the temperature decrements. The curve creeps toward the observed dip and stalls. Her advisor shrugs. Good. Now you know the limit of that lever. Across the hall, a void finder runs on a spectroscopic survey and flags a new hollow. They plot its edges, then its galaxies. A handful drift inside like campfires in a desert. It's not a mistake. It's the desert. If you're keeping our running theme in mind, the lesson is familiar. Where signals can travel, redundancy stabilizes facts. Filaments blaze with photons and get copied into many channels. Voids hold fewer messengers, they're low information by design. A cold patch that survives blind tests might whisper new physics. Most will settle into statistics. Until a pattern repeats, across instruments, across methods, with a significance that grows as you add data, the disciplined read is restraint. And yet one useful shift does land. Seeing emptiness as a feature changes how you search. You stop demanding uniform coverage and start asking what the edges tell you. In a holographic-leaning cosmos, boundaries matter most. Voids aren't unrendered. They're cheap on storage. The render cost shows up where the walls rise, where the gradients sharpen, where the light can carry a message and be heard. Quantum to classical, the universe locks in. We've been staring at structure, the web, the voids, the bright juveniles. Now zoom down into the rule that lets any of it become a stable fact. The universe doesn't wait for eyes. It waits for information to spread. When it does, possibilities stop interfering and start behaving like history. Down in the lab, the pattern shows up with cruel reliability. Send electrons through two slits and you get fringes until which path information leaks. Photons scatter off the edges. A molecule in the air jostles the beam. A detector clicks. The interference evaporates because the electron has become entangled with an environment that now carries a record. That's decoherence. It's not consciousness. It's bookkeeping. Amplitudes that once added now separate because their correlations have been broadcast into too many degrees of freedom to reverse. Scale that to the sky. Inflation stretched quantum fluctuations to cosmic size, but stretching isn't yet selecting. The lock-in happens as those modes interact with an enormous bath, photons, neutrinos, gravitons, and with each other under gravity. Modes that re-enter the horizon couple to the photon, baryon plasma. Their phases get imprinted in acoustic oscillations, then further copied as free-streaming photons carry the pattern across the sky. By the time recombination finishes, the microwave background isn't a superposition you could revive. It's a mural written redundantly in light. Quantum Darwinism turns that mural into a rule. Facts become objective when many fragments of the environment independently encode the same information. A dust grain's position is plastered into zillions of optical photons. A galaxy's mass distribution is stamped into weak lensing shears, X-ray gas, and thermal Sunyaev, Zeldovich signatures. Observers don't agree because they compare notes. They agree because they are reading different copies of the same environmental record. Objectivity is redundancy. The time scales are brutal. For macroscopic degrees of freedom, decoherence is effectively instantaneous. A micron-sized particle in air loses off-diagonal coherence for positional splits larger than optical wavelengths in about 10⁻31 seconds. In the early universe, number densities and coupling rates make the bath even more intense. The selection of pointer states, stable variables that survive environmental monitoring, happens far faster than any dynamical evolution we care to measure. In cosmology, those pointers are curvature perturbations with definite phases. Later, they're densities, temperatures, velocities. The variables you use in fluid equations are the ones the universe naturally preserves. So why does this matter for too big too soon? Because lock-in sets the rules the factories at dawn must follow. You can't rely on delicate quantum phases to coordinate collapse across cosmic distances. Causality and decoherence shut that door. Early efficiency has to come from classical channels, cooling routes, shocks, inflows, feedback cycles. The lock-in is why our fixes lived in messy gas physics instead of magic coherence. There's another stake. Horizons act like moving interfaces that gate what can be stabilized. Inside your particle horizon, signals can circulate and records can proliferate. Outside, nothing you do can copy information back to you. That's why the map of your universe is a mosaic assembled at light speed. It's also why the render cost is paid at boundaries. Facts that cross horizons, like CMB photons, become keystones of objectivity because their copies arrive from everywhere. Consider a micro story. A delayed choice quantum eraser in a basement lab toggles whether which path information is preserved after photons have already hit a screen. The interference returns in the sub-ensemble where the information is erased, but never globally. The lesson holds upstairs. Context determines which histories can recombine. In the cosmos, the context is an ocean of environment that never forgets. Once primordial modes are broadcast into the microwave sky, there is no sub-ensemble large enough to stitch them back. Lock-in also explains why anomalies are hard to trust. A genuine pre-inflation relic would need to survive relentless environmental monitoring and the averaging of cosmic variance. Most features that look special wash out because the sky is a master copier of typicality. When something persists, the acoustic peaks, the hemispherical asymmetry bounds, the exact blackbody, they persist because they are supported by vast redundancy. There's a thermodynamic price tag on all of this. Landwehr's principle says erasing one bit of information dissipates at least kT ln2 of heat. Turning quantum possibilities into classical facts isn't literally erasure, but the growth of entanglement and the proliferation of records increase entropy. The arrow of time in structure formation aligns with a monotonic growth in environmental bookkeeping. Galaxies remember their past not because stars keep diaries, but because the universe keeps copying their traces into photons, neutrinos, and tidal fields. Reversing that would require erasing every copy, a cost the cosmos refuses to pay. If you're keeping the ledger theme in mind, lock-in is the moment an entry goes permanent in your causal patch. Before selection, amplitudes are cheap and reversible. After, records are expensive and sticky. That's why late-time tweaks, reinterpreting photometry, correcting lensing, only move masses within error bars. The underlying classical facts are hard set by a billion environmental witnesses. And here's the pivot forward. If the universe stabilizes facts through redundancy inside horizons, then the ultimate limits on what can lock in, and how quickly, are set by those horizons. Finite patches imply finite storage and finite bandwidth. The next move is to treat horizons as the interfaces they are, boundaries that budget how much can ever be rendered into history. Horizons as interfaces, your bandwidth budget. If decoherence is how facts lock in, horizons decide how much can ever be locked in for you.